What I have on the breadboard is a 74 LS174. It's a hex D flip-flop, and you see the functional diagram here. As you'll notice, there are 6 D flip-flops. They have a common clear. The way I have it set is I have the odd inputs, that is 1, 3, and 5, tied to a 0, tied low. The others are floating high. What will happen is, when we clear it, all of these flip-flops will go to a 0 on the cue. So when we look at the circuit in a minute, you'll see that the only things that have a 1 on them are the VCC, the clock, and the clear bar. And then we're going to take clear bar to a 0 for a brief instant, and that will clear the registers. Then we are going to clock with a pulse, which will load the zeros into 1, 3, and 5. This is the clear, and it's already cleared. Now we're going to clock and watch the 3 lights should show up, and you see they do. One additional one here. This is VCC. This one, and this one. Now I'm going to reset it. And once again, the reset or clear is this pin. And so, well, to give you some motivation, or at least an idea of how designers use things like registers, I'd like to show you how a computer does arithmetic. This is a functional diagram of what is often called the arithmetic unit in a computer. This is a register, but it's a special register. It not only allows you to load data in on this load line, but it also allows you to shift the data by clocking this line. So basically, the way that a computer does arithmetic is this. It loads a value into this register. Then it transfers that value into a latch. And in this case, latch is the same as another register. I use a different name here so you won't confuse it with the shift register. But it's basically another memory. So you put the first number in here, then you put it down here. Now you bring the second number in. You now have 2 numbers, 4 bits in this and 4 bits in this. The 4 bits from this are brought into one side of an adder. The 4 bits from this are brought into the other side of the adder. The adder is a special circuit that we may talk about at some point, but basically what it does is it just adds these digits, this 4-bit number to this 4-bit number. This shows you how latches can be used, or registers, simple registers. What about this shift register? Why does it have a shift? Well, the reason is to do multiplication in binary. Remember that if you want to multiply a number by 2, a binary number, all you have to do is shift it one place to the left. So you can do multiplication by using a simple shift register as one of the input latches. So far, I've shown you a parallel register, that is the 174, LS174. Now let's take a look at a serial register like the one we just looked at in the arithmetic unit. Here is an SN74 LS165. I give you the full part number in case you need to look up a data sheet or something like that or would like to order one. Down below is the functional diagram. I have permanently wired the inputs so that we can use it both to load and to shift. The serial input is a 0, and then A, B, C, D are 1, 0, 1, 0 respectively. The clock inhibit is a 0. The shift load we can control and the clock we can control. And then E, F, G, H are 1, 0, 1, 0. To give you a little better idea of what's actually going on, I have repeated the serial input A, B, C, D, E, F, G, H over here. Now, what we will be doing is when we parallel load it, this data value, that is the 0, 1, 0, 1, 0, 1, 0, 1, will get loaded. Then we're going to take the shift load line to a 1, and at that time we can start clocking the register. And what will happen is it will shift this set of data out, and it'll appear on the output. Now the output illustrated by this LED. First we will load it, and the output should go to a 1, and it does here. We've also loaded in the word that is this data. Now let's clock it. As we clock it, what should happen is the 1 and the 1, 0, 1, 0, 1, 0 pattern should appear on this light. It's a 0. It's a 1. A 0. A 1. A 0. A 1. Now, if we keep clocking it, what do you suspect will appear on the outputs? Remember, the shift input is a 0. So we have now loaded this register and then shifted a 0 all the way through it. So now no matter how many times we clock it, it's only going to have zeros in it because we have, in essence, clocked all of the ones out. 3, 4, 5, 6, 7, 8, 9, 10. If this seemed a little bit much, what you might want to do is go back and play that part of the video again and watch any particular part of this circuit with having a data sheet like this one in front of you, which you can download from the TI website. Once again, I hope you've enjoyed this segment on latches and registers, serial and parallel. And I hope you'll stay tuned for part 4, in which we will move on and start looking at counters and some other logic as an introduction to a little bit of an overview on actually how people go about doing logic design.